So the context here is imagine that we have the paraboloid z equals x squared plus y squared from z equals 0 to z equals 16. So we have a piece of this paraboloid cup opening upwards. We have this vector field f, and we would like to compute the curl of f and do a surface integral of that curl across this paraboloid, where our paraboloid has been oriented with outward pointing normal vectors. The thing is, we're not going to do that at all. We are going to get to this computation using two kind of indirect routes. So first we will use Stokes' theorem, which I think is the more immediate of the two, to compute this surface integral using a circulation integral. Then I will show you a really neat other way to compute this using the divergence theorem. Our first approach is going to be to use Stokes' theorem, which tells us that this surface integral, this flux integral, can be computed using a circulation integral. So let me write that down, and then we'll dig into the details looking at the surface S. We would like to integrate the flux of the curl of a vector field across this surface S. According to Stokes' theorem, that's going to be equal to doing the circulation of F around the boundary of S. So this symbol here means boundary, so boundary of S. Okay, we have to make sure our boundary curve is parameterized correctly. For that, I think we should draw a picture. I would never do this kind of problem actually without having a diagram handy. So go ahead and sketch a paraboloid like that. Okay, that's the best I'm going to do. It is oriented with outward pointing normal vectors. So whenever you do Stokes' theorem, it's an oriented computation. You have to have a sense of direction. So this vector surface integral is called a flux integral. We need to know what direction we're measuring the flux across, and it's going to be outwards here. Okay, so this paraboloid is our surface S. The boundary curve is where we're chopping S off, which is in the plane z equals 16. Okay, making this look worse and worse. But the top of this paraboloid here is our boundary curve. That's going to be the domain for the circulation integral. You need to make sure that your boundary curve is oriented consistently with the surface, which means basically that you're satisfying a sort of right-hand rule. Let me sketch the orientation here, then I will tell you how to check this with your right hand, but I will not check it for you with my right hand right now because I'm worried that with the way this is being filmed, it's actually going to look backwards. So what you would need to do is imagine laying the finger, your index finger of your right hand, or all your fingers of your right hand, along the curve. Do so comfortably. So that's going to be this. This is my right hand. So the video is being flipped. It probably looks like my left hand, but this is my right hand. Okay, so I am going to do it, but just keep in mind here that what looks like I'm doing the left hand rule is actually the right hand rule. So this is my right hand, and I'm pointing my fingers in the direction of this paraboloid's boundary curve in a comfortable way so that my thumb is pointing outwards. That means traveling this way is the correct sense of orientation for this boundary curve. So again, my video is flipped. It looked like my left hand, but that was my right hand. My fingers lie in the direction of the boundary curve with my thumb pointing out like that. So our boundary curve has to be parameterized like this, which means that we are going, if this is the plane z equals 16, let me add some axes here. There's the y-axis, the x-axis, and the z-axis. This boundary curve is happening in the plane z equals 16. In that plane, viewed kind of in the standard way, looking down from above, our curve looks like it's going clockwise. That's not usually the way we travel around a circle whenever we parameterize a circle. So we have to be a little bit careful here. Let me write the parameterization here. I'm going to parameterize the boundary of our surface C using a parametric description. So this is going to be a parameterized curve. What's happening here is that z equals 16, but also for the paraboloid, z equals x squared plus y squared. So the circle is satisfying that x squared plus y squared equals 16. That means that the best description for this boundary curve is going to be 4 cosine of negative t because we're traveling clockwise. So this is reversing the direction. 4 sine of negative t, 16. Okay, so normally whenever you parameterize a circle in a plane, you almost always go counterclockwise. That's the normal rotational direction for a circle. And whenever you're parameterizing such a circle, you usually use cosine and sine and go counterclockwise. Here, we are going clockwise. That's why I made the angle negative. This is going to flip the sense of direction. And then the 4 here is indicating that the radius of our circle is 4, because x squared plus y squared is 16. And then the z-coordinate is just fixed at 16 because this whole curve lives in the plane z equals 16. So there's no other possible value for z here that would make any sense. Okay, let me clean this up a little bit. Cosine is an even function, which means that cosine of negative t is the same thing as cosine of t. So I'm going to write 4 cosine of t. Sine, on the other hand, is an odd function. So sine of negative t is negative sine of t. So this becomes negative 4 sine of t, and then z is 16. Okay, so that's a parametric description for the boundary of the surface, and this is going to be the curve that we do the circulation integral around. To do the circulation integral, we're going to need to compute f of the parametrized curve, so we do the composition f of r of t, and then we're going to dot that with the velocity vector r prime of t. So let me go ahead and write that here. R prime of t is going to be negative 4 sine of t, so I just differentiate each coordinate with respect to t. Negative 4 cosine of t, 0. Okay, let me actually write what we need to do before I start plugging in. All right, to evaluate the circulation of this vector field around this curve, we are going to now do an integral across the domain of the parameter t. I didn't write it down, but we're going one time around the circle. So our parameter t goes from 0 to 2 pi. So I'll go ahead and put that in for the balance of the integration. Then we are going to need to evaluate this by doing f of r of t dot r prime of t dt. Let me make a few comments and then I'm going to step away in case you need to take a break for a moment and think about all that we've done up to this point. F of r of t means plug this, or let me look at the simplified version, plug this in for the x coordinate in our description of our vector field. Plug negative 4 sine of t in for the y coordinate, and then plug 16 in for z. So that's doing f of r of t is let this be x, y, and z, and plug those into the vector field f. We're going to dot that with this vector, negative 4 sine of t, negative 4 cosine of t, and 0. Which means in a minute, when I come back and we start writing this out, I'm actually not going to be too concerned about what the third component of f of r of t is, because it's just going to be multiplied by 0. So that's going to be a nice simplification that we see when we start computing this. But let me pause for a moment, take a minute, and make sure you've got all of this ready to go, and then we will come back and finish this computation. We've done most of the conceptual work in this problem. We just need to finish this computation. So let's get going. I'm going to write it here. We are going to integrate from 0 to 2 pi. A vector which is the composition f of r of t. So let's write that down. The first component is 2y, where y is negative 4 sine of t. So twice this coordinate gives us negative 8 sine of t. The next component in the composition f of r of t is 2x, where x is, negative 2x, where x is 4 cosine of t. So that's going to be negative 8 cosine of t. Okay. And then the third component looks messy if you start writing it down, but actually we don't need to worry about it because we're going to dot this with the velocity vector whose third component is 0. So whatever I write here, it's going to get multiplied by 0. So let me just say kind of placeholder squiggle symbol. Okay, this is not this symbol, but it's going to get multiplied by 0. So I just don't care what it is. We are going to dot f of r of t, so that's what I just wrote down, with the velocity vector r prime of t. So that's negative 4 sine of t, negative 4 cosine of t, and 0. Okay. Let's do this dot product now. It's actually going to be really nice. I'll write it out and then we'll simplify it. Let me keep going here. Sorry, these computations kind of hard to squeeze all on the board in a really organized way, but we're still integrating from 0 to 2 pi. 32 sine squared plus 32 cosine squared. So 32 sine of t, that quantity squared, plus 32 cosine squared dt. Okay, so that's the result of doing the dot product, but sine squared plus cosine squared is 1. So this is really just 32. Which is wonderful. Integrating a constant over the domain from 0 to 2 pi is going to be 32 times 2 pi minus 0. So with Stokes' theorem, we're getting 64 pi. All right, let me step away, make sure you can read all of this, and then we will come back and solve this problem again using the divergence theorem. Now let's resolve the same problem, but this time using the divergence theorem. In order to use the divergence theorem, what we need to have is a surface which is entirely enclosing a region in R3. That's not what we're looking at here because this paraboloid does not enclose a region. We have a gaping hole at the top. However, we can add that and just call it a new surface. So let me give this paraboloid cup that we're looking at a lid. Imagine that we took this solid disk in the plane z equals 16, let's call this L, so that together S and L enclose this solid region now that's trapped inside of this cup. Okay, so our paraboloid is still named S, and the lid I just put on is called L, and together they are actually closing off a region in R3. That's what we would need to do in order to use the divergence theorem. If you forgot L, you're not positioned correctly to use this theorem. We also need to give L a sense of orientation, and for divergence theorem, it's always outwards. So we're going outwards here. We need to imagine going outwards with our oriented orthogonal vector for the new surface that we just created named L. What the divergence theorem tells us is that the flux of a vector field outward across the surface, which is enclosing a solid region, is equal to the divergence of that vector field across the region. So let me write that down for this problem, and then we will talk through that one more time because it's kind of a lot going on here with this curl of F sitting in our integrand. Okay, first let me name this enclosed region capital E. Then the flux of the vector field, which looks like the curl of F in this context, outwards across the boundary of E, because we have two piecewise put together boundaries here, we're going to add the flux across S to the flux across L. So this integral that we're actually interested in plus the flux across L of this vector field, which looks like the curl of F. Okay, so overall, that is the flux outwards across the boundary is equal to the triple integral over the enclosed region, so the solid 3D region E, of the divergence of this vector field whose flux we're computing. Here, it happens to look kind of funny. It's the curl of F. Okay, before I continue on with this computation, let me just say a few things. That is that the divergence theorem often does not present itself as a theorem that you use with a curl like this. So often you would see f dot ds equals a triple integral, or sorry, the flux of f dot ds equals a triple integral of the divergence of f dv. Here, the vector field f that we would normally see in the statement of the divergence theorem just happens to have a special appearance. It looks like the curl of another vector field. Okay, but this is still a vector field in its own right. So this is the vector field whose flux we're computing, and then over here we're taking the divergence of that vector field. Okay, so that's one remark. Another remark is if you're not sure what I mean when I say dv, you can think of that as like dx, dy, dz. I'm just not committing to any particular ordering with my differentials. See, what else is going on? Here we have two vector surface integrals or flux integrals. Here, this is just a plain old triple integral. Like I said a second ago, if I had differentials here, they would just look like dx, dy, dz. This is not a surface integral or anything like that. It's just a triple integral. Okay, and then there's one more very nice remark to make in this particular problem, and that's why I like to use the divergence theorem for this problem. That is that the divergence of a curl is 0. You can check it if you like with this vector field we have. So given f, you can compute its curl, then compute its divergence. So do the curl, then the divergence of that, you'll get 0. I don't need to check it. I know it's going to be true. Okay, so that's a theorem. Which means that the whole right-hand side here is 0. We're not going to do this triple integral at all. It's 0. So what this problem is actually going to have us do is solve for this flux integral by solving this one and negating it. In fact, to save room, let me now mention this whole thing is 0. Okay, so just ignore that. Maybe I'll erase it once we get going. The vector surface integral we want to compute, we can now think of as -1 times this vector surface integral, which is actually going to be a nicer integral to compute because L is a solid disk in a plane. It's just going to be a nicer domain. So let me pause for a second. And what I would like for you to do before I come back is write down a parameterization for the solid disk of radius 4 in the plane z equals 16. Okay, so we need to parameterize this lid L. This is a solid disk of radius 4. That means we're going to use a polar approach to parameterization, but we also need to consider not just a rotating angle, but an expanding radius. We have to fill in this disk from 0 to radius 4. So it's a solid disk. You need 2 parameters whenever you parameterize a surface, and for us, those parameters are going to represent the radial component and the angular component in the solid disk. Okay, that was a lot of words. Let me write it down. The parameterization for L that we should use looks like u cosine of v, u sine of v, and then z is stuck at 16. There's no other choice for z. So in this parameterization, u represents the radial coordinate, and that is going to expand from 0, which gets us on the z-axis, out to 4. So 0 is less than or equal to u is less than or equal to 4. And then we need to go all the way around. So the angular component, which I'm calling v here, is going to go from the standard 0 to 2 pi. Okay, so that's the parameterization for the solid disk. In order to do this vector surface integral, we now need to create the vectors I call r sub u and r sub v, and then cross them. Okay, r sub u is going to mean differentiate each component with respect to u. So that's going to be cosine of v, sine of v, and 0. R sub v is the same idea, but we differentiate with respect to v. So that's negative u sine of v, u cosine of v, and again 0. When you're doing these flux integrals where you write down r sub u and r sub v and cross them, I always recommend stacking them like this so that you're ready to go with the cross product. Let me call that vector n. Cross these, the first 2 components I know are going to be 0, but let's just verify it. So the first component is sine times 0 minus u cosine times 0, so that's 0. Second component is 0 times negative u sine v plus or minus cosine v times 0, 0. And then the third component is u times cosine squared plus u times sine squared. So overall, that's u. I'm doing the Pythagorean identity simplification there out loud. So 0, 0, u. How did I know the first 2 components were going to be 0? Because there's only one sense of direction perpendicular to the surface, and it's vertical. So whatever vector we got here, it either had to be pointing up or pointing down. We want to make sure it's pointing up to match the orientation that we gave our surface in order to apply the divergence theorem. We wanted to say this is oriented with an upward pointing orthogonal vector. U here ranges from 0 to 4. That's the domain for this parameter u, which means that this third component is never going to have z negative. We're never going to be pointing down. So overall, this vector does point up, just like we want it to. So we're good to go. Okay. Now we are just going to do a vector surface integral, vector surface integral. There's a lot of words in this problem. Vector surface integral, which means that I need to compute the curl of f and then evaluate that on this parameterization, and then dot that with this vector. But notice that we have zeros in the first two components, which means when I compute the curl of f, I don't care what the first two components are. I only care what the third one is, because the first two components are going to get wiped out. We could actually do this all inside the integrand because it's such a nice computation when you actually crunch the numbers. But let me do the curl of f right here. Keeping in mind that the first two components are going to get wiped out by zeros. So that's don't care, we need the third component. All right, so the third component is going to be ddx of the second component. So it's like a cross product computation. So ddx of the second component is -2 minus ddy of the first component, which is 2. So -2 is overall -4. Okay, let me say what I did here. This was dx, let's see, what should I say? If f has components capital P, capital Q, capital R, this was q sub x minus b sub y. Okay, that's what I did. All right, so our curl has coordinates which would not be 0 actually, but we don't even care what they are. And then the third component is really nice. It's just -4. So that when we do this vector surface integral, we're now ready to go. We're going to integrate from 0 to 2 pi, then from 0 to 4. This vector field where we would need to plug the parameterization in. So if I had terms here that looked like x, I would put in u cosine v. If I had terms that looked like y, I would put in u sine v. And if I had anything here that contained a z, for z, I would put in 16. That's how we would compute the composition of the curl of f on this parameterization. But we don't have to do anything because actually the only component we need is constant. So something, something, -4. Okay, so that's the curl of f evaluated on the parameterization. Now we need to dot that with this orthogonal vector 0, 0, u, du, dv. Now it's a double integral. And overall, the integrand is just -4u. Let me see if I can continue that here. We're going to say it's this leading negative times 0 to 2 pi, 0 to 4, -4u, du, dv. Okay, so let's just go ahead and get rid of those negatives. Okay, I'm going to step away. See if you can finish this, get to 64 pi, then I will come back and finish the computation. Since there's no v dependence in the integrand and our double integral has constant bounds, let me go ahead and peel off the v integral, and then we would be integrating 1 dv from 0 to 2 pi. So basically there's a leading 2 pi. And then anti-differentiate this with respect to u, we're going to get 2u squared from 0 to 4. Okay, u squared is 4 squared is going to be 16, times 2 is 32, times 2 is 64, times pi minus 0. Okay, so hopefully that's what you got as well, which is good because it means the math was consistent. Whether we use Stokes theorem or divergence theorem, we got to 64 pi. I think Stokes theorem was probably the more natural approach for this problem. With divergence theorem, there was the extra step of adding in this lid. But I liked the divergence theorem just because it gave us a chance to see that the divergence of a curl is 0. So there was kind of a neat way to compute this flux integral by doing a different flux integral. And I just wanted to bring that up.